Hello, everybody. Today we're going to be talking about the gas laws. And what the gas laws are, they're mathematical relationships between different variables such as pressure, volume, temperature, and even the amount of gas, which we measure in moles. Of the different gas laws, we're going to take a look first at one called Boyle's law. And this gas law is a relationship between pressure and volume. And during this mathematical relationship, there's going to be a constant. The temperature here is going to be constant. And what the law says is that when you compare pressure and volume, there is an inverse relationship. And what that means is that when the pressure increases, the volume decreases, or vice versa. If the pressure decreases, the volume goes up. Now, this is occurring while the temperature is being held constant. So think about a balloon, and if you were to squeeze a balloon, what would happen to the pressure inside the balloon? Well, the answer is if the volume decreases, the pressure inside the balloon would increase. And then vice versa, if you would allow the balloon to expand, then as the volume is increasing, the pressure would go down. Now, the reason for that has to do with collisions. See, when you decrease the volume, you're bringing the molecules closer together. So what happens is if there's less space, the molecules themselves will collide more often. More importantly, they'll collide more with the walls of the container. Anytime that you increase the number of collisions, the pressure will increase. And that is why lowering the volume will increase the pressure. There's a mathematical relationship when using Boyle's law. If you look here, P1V1 equals P2V2. What that means is that the initial pressure times the initial volume is equal to the final pressure times the final volume. Now, earlier I had said this relationship is inversely proportional. Here's a graph that illustrates that. Notice on the x-axis, as the pressure, and you can see this as the pressure is increasing, notice on the y-axis, the volume is going down. So you'll see the inverse relationship that this graph illustrates. So as pressure increases, volume is decreasing. Now mathematically, we can go ahead and do a calculation using the formula P1V1 equals P2V2. Here we have an example problem where a cylinder is equipped with a movable piston, has an applied pressure of 4.0. So let's go ahead and write our givens here. So the initial pressure is 4 atmospheres. And they tell you that the volume, the initial volume, is 6 liters. So what's going to happen here is we want to know what would be the volume of the cylinder. So let's put here V2. We're looking for the final volume. If the applied pressure, so here's the new pressure, is 1 atmosphere. Okay? So the equation for Boyle's law is P1V1 equals P2 times V2. We are looking for the final volume. So when you do the algebra, P1 times V1 divided by P2 will give us the final volume. Now, we did the algebra already. Let's substitute our values. So the original pressure is 4 atms. The original volume is 6 liters. When you divide that by 1 atm, which is the final pressure, what happens is this will allow us to calculate the final volume. You'll notice that atms cancel. And then when you do the math and we round this to 2 significant digits, you're going to get that the final volume is 24 liters. I rounded that to 2 significant digits. Now notice, if the pressure goes down, the volume should go up. And if you look at the math, this confirms it. The pressure went from 4 atms to 1 atm, while the volume increased from 6 liters to 24 liters. So the math confirms the theory. Let's take a look at a second gas law. This one's known as Charles' law. And this is a mathematical relationship between volume and temperature. This time, the pressure is going to be the constant. You're going to notice that whatever is being held constant will not be part of the mathematical formula. Now, what's important about all the gas laws, starting with Charles's law, is that they are all related with temperature being at the Kelvin scale. So if you're given a problem in which the temperatures are in Celsius, you must convert it to Kelvin. You cannot do the math unless the values are in the Kelvin scale. And if you recall, to go from Celsius to Kelvin, you simply add 273, as you can see right over here. And the relationship is directly proportional. You see, if the temperature goes up, so will the volume. They both increase in the same direction. So keep that in mind, okay? Remember that 0 Kelvin, which is equal to negative 273 Celsius, is referred to as absolute zero. Now let's talk about why increasing temperature causes volume to increase. Well, what happens is if you have a container, and in order for that container to maintain its pressure constant, the way to do that is for the container to increase in size. So think of like a tire on a hot day. Your tires actually expand because on a hot day, the temperature is higher. So the tire will expand, not a lot, but it will expand. And on a colder day, it will contract. Okay, if you look here, I wrote that heating a gas will cause expansion of a gas. The same can be applied to a balloon. Okay, if I were to put a balloon, let's say in a refrigerator, it's actually going to cause the balloon to constrict, to contract. The volume will get smaller. Now notice the mathematical equation is V1 over T1 is equal to V2 over T2. In other words, the initial volume divided by the initial temperature is equal to the final volume divided by the final temperature. Now remember, the temperatures must be in Kelvin. Okay, so before you do any math, make sure they're in the Kelvin scale. This is a graph that shows you Charles's law. Notice this graph, both factors, volume and temperature, are increasing, okay, because they are directly proportional. Notice as the temperature goes up, so does the volume. And keep in mind, although it says Celsius down there on the x-axis, it must be in the Kelvin scale. I cannot stress that enough. So, with that being said, let's take a look at a calculation using Charles's law. So according to this problem, you have a piston that has an initial volume of 88.2 milliliters. Let me write that here. And it is being heated from an original temperature of 35 degrees Celsius to a final temperature of 155 degrees Celsius. They want to know what would be the final volume. Notice pressure isn't even mentioned in this problem because it's constant. So if it's not mentioned, you can assume it's constant. Sometimes they'll tell you it's constant in the problem. Now, before I start, I'm going to go ahead already and change these two temperatures to Kelvin because the math has to be with these values in the Kelvin scale. So I'm going to add 273 to each. The formula for Charles' law looks like this. And what we're going to do is they're asking us to find final volume right over here. So one good way to do this is if you cross multiply these two and then divide by T1, and I'll show you how to do the algebra here. If you cross multiply, that will be V1 times T2, and then you divide by T1. That's a good way to isolate the final volume. So at this point, we can simply plug in the numbers, okay? So our initial volume is 88.2 milliliters. Our final temperature, and that's why it's important to label all your givens, is 428. And then we're going to divide that by 308 Kelvin. Now that's going to give us the volume. And what ends up happening here is you'll notice how the units cancel. And when you do the math and you multiply and divide, you're going to get 122.56. What we're going to do is let's use 3 significant digits. When you convert to Kelvin, you'll notice you got 3, 3, and you got 3 over here. So our final volume with 3 significant digits is going to be 123 milliliters. Now, notice, if the temperature goes up, which it did, the volume should go up. And if you look at the math confirms the theory. They both go up. Okay, they are directly proportional. Now, let's take a look at the third gas law, Gay-Lussac's law. This time, we're going to compare pressure and temperature. And what we're going to do is we're going to keep the volume constant. So you'll notice the volume will not be part of the mathematical formula. And in this relationship, both temperature and pressure are also directly proportional. Again, the temperature must be in the Kelvin scale, so make sure we switch Celsius to Kelvin. Now, it says that the pressure goes up when the temperature goes up. This again has to do with collisions. The reason the pressure goes up is because an increase in temperature causes the molecules to move faster. In other words, their kinetic energy increases because kinetic energy and temperature are directly proportional. So, if the molecules are moving faster, 2 things are going to happen. They're going to collide more often either with each other or, more importantly, with the walls of the container. Not only are they going to collide more often, they're going to also collide with more momentum, more force. So when you combine that there's an increase in the momentum of these collisions plus an increase in the frequency of collisions, that is why the pressure will go up. Anything that can cause the frequency of collisions to increase will cause the pressure to go up. Now, the formula for this, similar to Charles, but notice volume is not part of the formula. It's P1 over T1 is equal to P2 over T2. In other words, the initial pressure divided by initial temperature is equal to final pressure divided by final temperature. Okay? So, a graph illustrating Gay-Lussac's law is similar to the graph from Charles' law. They are directly proportional, so you'll notice here that as the temperature goes up, so does the pressure. Okay, and conversely, if the temperature goes down, the molecules will move slower, so there'll be less collision, so the pressure will go down. So this gas law is also directly proportional. So here we got a sample problem where you got a sample of nitrogen and they give you the volume, and we'll call it 45 milliliters. And they're telling you that at this volume is at 27 degrees Celsius, and they give you a pressure of 600 torrs. They want to know what would be the pressure if we cool this gas to negative 73 degrees Celsius. But notice it says that the volume remains constant. So we're not going to use volume at all in this problem. If it's constant, that means that variable stays the same, so it's not part of the math. Now again, one of the things I recommend is change your temperatures if they're in Celsius to Kelvin. Okay, so we got 300 there, and this is negative 73, so when you add that, it's going to come out to 200 Kelvin, so we did that. And if you remember, the formula is P1 over T1 equals P2 over T2. We are being asked to find the final pressure. Okay? So, again, if you cross multiply and then divide, it'll be P1 times T2 over T1 will give you the final pressure. So, now that we did all our conversions, let's substitute the numbers. Our original pressure is 600 torrs. Our final temperature is 200 Kelvin. And we're going to divide that by the initial temperature, which is 300. Now, we're cooling this gas. This will give us the final pressure. And if you recall here, let's eliminate this. And you'll notice that the answer is going to be 400 torr, okay? And that'll be our final pressure. And I'm going to leave it with one significant digit because the 600 is the variable there that only has one significant digit. Now notice, if you look here, the temperature went down. So notice that the pressure should also go down, and the math confirms the theory. So this is a Charles' law problem. Now, what about if we had a situation where neither pressure, volume, nor temperature were constant? The only thing constant was the amount of particles, which is measured in moles. Well, then we're talking about something called the combined gas law. And here, the relationship is between pressure, volume, and temperature. The only thing being held constant is the amount of gas. That's the only thing that is fixed, which is the moles. Now, the equation for this is a little bit more complex. Notice it's P1 times V1 over T1 is equal to P2 times V2 over T2. Now, one of the things I like to tell my students is if you cross multiply these two parts and you cross multiply these two parts, mathematically they're equal to each other. Let me show you. I'm going to make this linear so that the algebra is a lot easier. If I cross multiply P1, V1, and then with T2, that would be equal to T1 times P2 times V2, and what I did is I got rid of fractions. I made this equation linear, and you're going to see this is a lot easier to manipulate algebraically than the original equation. So this is a great equation to use when solving a combined gas law problem. So let's take a look. Here we have a problem. Now, how do you know when to use this? Well, usually there's 6 variables. They're going to give you 5 out of the 6. When you see that pressure, temperature, or volume, any one of those is not constant, and they give you those values, you're going to have to use the combined gas law. So let's do the following. Let's read this problem, and as we read it, let's write the variables. So according to this, we got an initial volume here of 158 milliliters. They tell you that the pressure is 735 millimeters of mercury, and they give you the temperature at 34 degrees Celsius. Now, the gas is being compressed to 108 milliliters. It's being heated to 85 degrees Celsius, and they want to know what would be the final pressure, and we want that in millimeters of mercury. Let me fix this here. Okay, so we want this in millimeters of mercury. Now, what I'm going to do right off the beginning here is let's go ahead. We're going to need to change this anyways. Let's change these to Kelvin. This one's going to be 307. This one's going to be 358. And earlier I had shown you the original equation. We know it's P1 V1 over T1 is equal to P2 V2 over T2. But I'm going to show you that trick. When you cross multiply these two, you get P1 V1 T2. And when you cross multiply these two, you get T1 P2 V2. Okay, you're going to see they're equal to each other. Now, we're looking for the final pressure. So, look how much easier this is to manipulate. So, you go P1 V1 over T2 is equal to T1 over V2. It's much easier to isolate this, and you get this here. Now, we're ready to plug in our numbers. So, let's go ahead and do that. Let me get that out of there. So, P1, if you look at our information, is 735 millimeters of mercury. V1 is going to be, and this is the importance of setting up everything nicely, being organized, writing all your givens. And then T2 is 358 Kelvin. And then we're going to go ahead and divide that by T1, which is 307, and that's Kelvin. And this is 108 milliliters. Now, all of this is going to be equal to P2. And if you look at units, okay, we're looking for the final pressure. The kelvins and the milliliters are going to cancel. Now, when you do the math, the numerator, if you multiply the top three numbers, you get 41574540. I did that on my calculator. And then the denominator is 33156. So when you divide those numbers with each other, you're going to get a final answer. And what I'll do here is I got 1,253.9 millimeters of mercury. What I'm going to do is I'm going to round this to three significant digits. If you notice, even though this started with 2 here, when you change it to Kelvin, you got 3. So 3, every number in our mathematical formula has 3 significant digits. So you can either put 1,250 millimeters of mercury, or you can put that in scientific notation, which would be 1.25 times 10 to the third millimeters of mercury. And that will be your final answer for the final pressure. Okay? So that was the combined gas law. Now we have one more that we're going to look at. And this next one is known as Avogadro's law. And here what we're doing is we're comparing the amount of gas in moles with volume. And according to this law, it says that a volume of gas is directly proportional to the number of moles. Now, there are two constants here. This relationship is true, but temperature and pressure are constant. You're going to see again that whatever is being held constant will not be part of the mathematical formula. And this equation, you'll notice that moles and volume are directly proportional. Think of a balloon. If I were to blow air into a balloon, what I am doing is I'm increasing the amount of air that I'm introducing into the balloon. I'm adding more moles. The more air I put in, or the more moles, the balloon in response inflates. It increases in volume. If I were to remove air from a balloon, the response is that the balloon will shrink. The balloon will deflate or decrease in volume if I remove air or moles from the balloon. So that's the relationship between the two. This relationship is also directly proportional. Here's the formula. Notice that pressure and temperature are not part of the formula. According to this, the original volume, V1, divided by N1, N being the symbol for moles, is equal to V2 divided by N2. Now, be very careful. If a problem is in grams, you must convert it to moles. This formula, the numbers have to be in mole units. Okay? And in order to go from grams to moles, if you recall, what you do is you get the mass in grams, and you got to divide that by the molar mass or atomic mass, if it's an atom, to get to moles. Just remember that some of the gases are diatomic. For instance, if it's oxygen gas, which is diatomic, the molar mass would be 32 grams per mole. So keep in mind that some gases are diatomic. Okay? So, here we're going to take a look at a sample problem. And by the way, the graph will also look like the graph for Charles' law and Gay-Lussac's law, since they're both directly proportional. As the moles increases, the volume will also increase. Now here we have a problem where it says a 4.8 liter sample of helium gas contains 0.22 moles of helium. So let's write this information down. So they're giving us the volume, 4.8 liters. they're telling you that the moles, so we'll call that N1 for moles, is 0.22. This is, it's already in moles, so we don't really need the molar mass of helium for anything. Now, notice, how many additional moles of helium gas should you add so that the volume increases to 6.4 liters? Okay, so they're asking you for additional moles, not final moles, but additional moles. This is a little tricky in the wording. Notice they tell you the temperature and pressure are constant. So the formula is V1 over N1 is equal to V2 over N2. We are looking for N2. Again, we're going to cross multiply these two, so it'll be N1 times V2, and then we're going to divide by V1, and that'll give us the final moles. Okay, so when you plug this into the equation, you got 0.22 moles times V2, which would be 6.4 liters, final volume, over 4.8 liters. And what's going to happen here is the liters will cancel. This will give us the final moles. And the answer we get is 0.29. Now, normally this would be the answer to a problem. But they don't want the final moles. They want to know how many additional moles. So here's what we got to do. We got an extra step. We know that the new volume will have to be 0.29 moles. We started with 0.22 moles. So if you subtract the final volume, the final moles that you just calculated by the original number of moles, if you do this like that, and you subtract, the difference is 0.07 moles. This number right here is how many moles we would need to add to get to 0.29. So there was an extra step. Most of the time, they just ask you what would be the total number of moles that you need to add, and the answer would have simply been 0.29 moles. But since they're asking you how many additional moles needed to be added, we needed to subtract in order to get this answer over here, 0.07, and that's how many more moles we would have to add to get to 0.29 moles. Okay? This will conclude our gas law unit. So as you saw, we went over Boyle's law, Charles' law, Gay-Lussac's law, the combined gas law, as well as Avogadro's law. I will do a review using the combined gas law to show you how that relates to the other laws, and then I will introduce a new gas law called the ideal gas law. So I hope that this lesson helped.